Welcome to the second Bhaumik lecture of the year. I'm very pleased that Kip Thorne is able to give the lecture today. He's a professor emeritus at CalTech. He was the Richard Feynman Professor of Theoretical Physics at CalTech. He's a renowned expert in general relativity, black holes, wormholes, and of course gravitational radiation. He's won many awards, which I'm not going to list because there happens to be one award that stands out, and that's the 2017 Nobel Prize in Physics that he won with Ray Weiss and Barry Barish. The citation reads, "For decisive contributions to the LIGO detector and the observation of gravitational waves." And it's, of course, very inspiring work, and at the Bhaumik Institute, we're going to start a research program on precision calculations of gravitational waves. Besides, of course, winning the Nobel Prize, he happens to be one of the coolest physicists alive. And if the proof is, if you have not seen the movie Interstellar, you should go see it, and then go look for the name of the robot called Kip. Anyway, I give you Kip Thorne, who's going to tell us about gravitational radiation.
If you've seen the movie, you may know that the robot Kip manages to kill the only theoretical physicist who's on board the mission. So when Christopher Nolan contacted me wanting to know could they name the robot after me, and he reminded me of what the dastardly deed the robot did, and I said, that's fine, that's fine. So anyway, I was invited to give this lecture and decided instead of talking about gravitational waves, they will be a small part of this. I'd rather like to talk about something else that is near and dear to my heart, a piece of physics and beginning to be a piece of astrophysics that is not well known, but I think is very exciting. So this lecture has some very technical components, and so physicists in the audience and some other physical scientists and engineers may appreciate them. And I'll ask the rest of the audience to be patient as I go through some technical pieces. But I'm aiming it for a broader audience than just the physicists and physical scientists and engineers. I have found that since this prize, I seem to draw people who are beyond the usual audience for this kind of a talk. Anyway. So the topic is geometrodynamics, by which I mean the nonlinear dynamics of warped or curved space-time. And the story begins with John Archibald Wheeler, who was my PhD advisor at Princeton University. I went to Princeton in 1962 to begin working with him, beginning about 1958, which is 60 years ago, and extending up through about 1968 for 10 years. One of the central features of the research that he and his research group were doing and that of his enthusiasm was geometrodynamics. And here he is lecturing on geometrodynamics about 1968. And his lectures, he would go in before the lecture and he would cover the blackboard with colorful chalk, and he would basically talk about the things he had put on the blackboard. This was on the occasion of Willie Fowler's 60th birthday. Willie's down here. Willie was a CalTech professor who got the Nobel Prize for explaining the origin of the elements inside stars. So John told us that the most interesting aspect of general relativity that we could possibly ever study, aside from its interface with quantum theory, the so-called laws of quantum gravity, would be geometrodynamics. And by this he meant that that space and time, according to Einstein, are warped or curved. We see that warping or curvature in the solar system. The space around the sun is slightly curved, and That's been measured with very high precision. Time slows a bit on the surface of the Earth, a slowing of time or warping of time due to the Earth's mass. We have lots of very high precision measurements of this. But he said what would really be interesting would be if you had no matter present, you just had warped space-time. What's it being warped by? By the energy of the warping. The self-interaction, the veritable snake eating its tail. The warped space-time that was highly nonlinear, which meant very, very strong, and highly dynamical, changing very rapidly. And the idea was, for example, at that time, it's as though we had only seen the surface of the ocean on a very calm day, but not in a storm. And the surface of the ocean is like space-time. And in a storm, it gets really riled up, and space-time gets really riled up with a very rapidly changing rate of flow of time, tremendous contortions in the shape of space, dragging space into whirling motion by vortices that I'll talk about. He said, we need to understand this. It would be very interesting to understand this. What does general relativity say about it? And can you do observations of this and explore it? Things that don't involve matter. The nonlinear dynamics, then, of curved space-time. And I remind people who are working in physical sciences or engineering, the nonlinear dynamics elsewhere in physics plays very interesting roles. It's responsible for and is involved in fluid turbulence, tornadoes. There are phase transitions in condensed matter that arise from nonlinear dynamics. Nonlinear optics, that is modern optical technology. Colliding solitons or solitary waves in fluids and in plasmas, in nonlinear crystals and optical fibers. And in mathematics, chaotic maps, strange attractors. These are all phenomena that arise from nonlinear self-interaction of some sort of field, and that are really fascinating to behold. And so I and John's other students and postdocs and colleagues tried to study geometrodynamics, the nonlinear dynamics of the geometry of space and time. And for 4 decades, we had an effort that was tremendously frustrating. We had in our hands only analytical techniques, trying to solve Einstein's equations of general relativity to explore this phenomenon with pencil and paper and equations. And it's so complicated to understand that we made very, very little progress. Wheeler foresaw this, and so he encouraged his colleagues, his students, to develop techniques to solve Einstein's equations on computers, numerical relativity. And the pioneering work on this was in the 1950s and early 1960s by John's students, particularly Richard Lindquist and Charlie Misner. And it took 4 decades to bring numerical relativity to near fruition so you could start getting really interesting things out around the year 2000. And another 15 more years for it to near maturity so you could really explore geometrodynamics in its full glory. And I'm going to be telling you what we've gotten out first from analytical techniques, what little we were able to learn, and then about what we've learned from numerical simulations and going back and forth between simulations and observations. Now I'll talk about 4 arenas for geometrodynamics. Geometrodynamics near singularities. I'll explain what a singularity is. The nonlinear self-coupling of gravitational waves to produce what's called critical gravitational collapse. These are buzzwords for you at the moment, but I'll explain what this means. Colliding black holes, creating a storm in the shape or the geometry of space and time. And then gravitational wave observations of geometrodynamics. We're beginning to do observations to explore this phenomenon. And so that's where I'm going. So let me begin with geometrodynamics near singularities. And this story begins with Robert Oppenheimer and his student Hartland Schneider, who was a truck driver from Utah and went to Berkeley and was real bright. And he got into Oppenheimer's orbit. And together they solved Einstein's equations for the implosion or collapse of a star in which somehow all the pressure had been removed in order to make this easy to solve. And it was a spherical star. and it imploded to form a black hole. Here's the horizon of the black hole, and at the center of a black hole, a singularity. The singularity then is a place inside the black hole where tidal forces, which are a key aspect then of geometrodynamics, are ultra strong. So if I put my wife, Carolee Winstein, who's not here, but she'll come after at the end of the lecture. She's heard this stuff before. If I put her up above the black hole, then the gravitational pull on her feet is bigger than on her head, and so she gets stretched from head to foot. And there's a squeezing force also from the sides, and these are what are called tidal forces. And these tidal forces are the things that produce the moon, the tides on the Earth, where the source of those tides, or the tidal forces, is the moon and the sun. And so right at the singularity, the tidal forces are infinite, and so Carolee gets stretched infinitely. And of course, she's dead by then. The atoms of which her body are made also get stretched infinitely, and we don't really know what happens. So the actual physics of the core of the singularity is governed by the laws of quantum gravity, a holy grail of modern theoretical physics, which we don't really fully understand. We're only beginning to understand. I gather Ed Witten gave one of these lectures, and I presume he talked about aspects of that quest. He's been perhaps the world leader in that for some years. In the 1939, after Oppenheimer did this analysis and saw a black hole form, though the phrase black hole had not yet been invented, and the singularity at the center, there was great skepticism as to whether this is what would really happen in the real world, because this imploding star in Oppenheimer's calculations was absolutely spherical. And if it was not spherical, it was reasonable to expect that stuff would go in, it would whirl around near the center and fly back out. But it would manage to avoid forming this singularity. After all, a singularity is a place where the laws of physics as we know of them break down, where general relativity fails, and where you have to have new laws of physics, the laws of quantum gravity, to understand the core. And so there was great skepticism about whether the singularity was something that would really occur in nature. And so I want to tell you a bit of the history of this, because it's leading up to geometrodynamics. Yevgeny Lifshitz and Isaac Kalatnikov, close friends of mine, in Moscow in 1960, they did a detailed analysis, a deep mathematical analysis of Einstein's equations, and came to the conclusion that you would not form singularities ever in nature, in reality. And this got codified in the textbook from which I learned relativity, the classical theory of fields, by Lifshitz and his mentor, Lev Landau. These are really the great Russian physicists of their generation. In there's a section 110 on cosmological problems, where the section is titled "The Absence of Singularities in the General Cosmological Solution." Basically, they purported to prove that you cannot form singularities in reality, that deviations from spherical symmetry will always guarantee you don't get them. A few years later, Roger Penrose in London introduced a new branch of mathematics into relativity. It may have been the first major use of it in theoretical physics, differential topology. I won't talk about what this is, but it has to do with connectivity of things as opposed to shapes of things. And so the handle on a cup is a topological phenomenon. But anyway, he introduced this new branch of mathematics, and he used it to show, and here's the buzzwords, that time-like world lines end inside of black holes under a reasonable set of assumptions about the nature of matter. What that means more heuristically is if you fall into a black hole, you cease to exist. But he couldn't say what happened to you. He couldn't say anything about geometrodynamics. He just proved that you cease to exist, that time-like world lines cease to exist inside black holes. This created enormous consternation in Moscow. So the Landau School of Theoretical Physics, they were really great they recognized that there were a whole new set of tools here being used, and they could look at this and learn the tools and see that what Roger was saying. I understand Roger was also here and gave a Bhaumik lecture recently. What Roger was saying was a very powerful statement that could well be correct. And so they reconnoitered for a period of about 4 years. In 1969, I went to Moscow. I was shuttling back and forth between Russia and the United States in that era. It was the beginning of an era of shuttling back and forth during the Cold War, collaborating with Russians on research. And Yevgeny Lifshitz, shown here, gave me a manuscript to hand carry out and submit in their behalf to Physical Review letters, in which they conceded that they were wrong. And he said, I don't want to wait for the censors to okay this for publication. It's obviously not secret research, and I just want to get it out and get the confession out into the world, and also to explain that what we have discovered together with our young colleague Belinsky is not only that we made an error, but we have discovered the nature of geometrodynamics near the singularity, the first big breakthrough in geometrodynamics. And so I smuggled it out. It was published in Physical Review letters, and it ignited a firestorm in the West, as I'll explain. But this is from a party 2 years later in Kalatnikov's house. So this is me, John Wheeler, Yevgeny Lifshitz, Isaac Kalatnikov, and Vladimir Belinsky. And so what I'm telling you is stuff sort of that I lived through and with dear friends. And so what did they do? Well, and now I'm going to get just a little bit technical. They did an approximate analysis, not an exact analysis. They used various approximation techniques to, first of all, argue quite cogently that the singularity, the generic singularity you would run into is space-like, which just simply meant that if you got near it, there was no way to avoid it. No matter how fast you moved, you would get caught by it. And that as you got near it, if you're going up here, and this is time plotted up and space plotted horizontally, as you move forward or upward in time, you lose contact with your neighbors. And there's no longer any possibility for your neighbors to have any causal influence on you. And so the Einstein field equations, which are partial differential equations, become asymptotically ordinary differential equations as you approach the singularity. And being ordinary differential equations, they were soluble by standard techniques. And so this was the big deal, that they was showing this spatial decoupling. And they concluded that the temporal dynamics, the geometrodynamics, is something called Mixmaster, which had been discovered independently by Charlie Misner, Wheeler's student in the US, and Belinsky and Kalatnikov. They had discovered it for situations that are totally homogeneous, not a situation where you have completely random initial data, initial conditions, but this had been discovered for homogeneous situations. And the statement was that different versions of this Mixmaster behavior will be seen by you as you hit the singularity, or by me as I hit the singularity, or by my wife as she hits the singularity, because of the decoupling. So what is the Mixmaster behavior? This is quite interesting. So let's imagine that I fall into the black hole, and I meet the tidal forces that stretch me from head to foot and squeeze me from the sides. But then those tidal forces begin to oscillate. And so I'm initially stretched in this direction, squeezed in that direction. Then I'm stretched horizontally and squeezed vertically. Then I'm stretched vertically, squeezed horizontally, faster and faster and faster. And what is a chaotic pattern governed by what a mathematician would recognize as a chaotic mathematical map, so a so-called continued fraction map, it's sometimes called. And in fact, this pattern of stretching and squeezing I can describe in terms of a diagram. Stretch and squeeze, they're in the east-west direction, for example. You have a continuous squeeze that's down that gets stronger and stronger and stronger. While in the up-down direction, you've got a stretch followed by a squeeze, followed by a stretch, followed by a squeeze. And in the north-south direction, a squeeze, squeeze, stretch. And this goes on for a little while, what's called, they call an era, where these are cycles of stretch and squeeze. And then the axes, the directions of stretch and squeeze, rotate in some manner. And they give a formula for that rotation. They rotate in some manner, and then a pattern starts all over again. And then the axes rotate, and then pattern starts all over again. So basically, in some sense, like a taffy pulling machine, where the taffy pulling machine turns over on its side and then changes its orientation every now and then. These era transitions are driven by spatial curvature for physicists, and as I said, it's governed by a chaotic map. There was great skepticism of this predicted geometrodynamics in the West. By the West, I mean outside of the Soviet bloc of countries. Great skepticism because of the approximation techniques that were used to derive it. The standard phrase that I heard all of my colleagues, particularly in the UK and the United States, say is, this is the Belinsky-Kalatnikov-Lifshitz BKL conjecture that has been made with the use of heuristic arguments. And that was the attitude in the West until numerical relativity became sufficiently mature that you could begin to do calculations with it. And when that happened, then a number of numerical relativity experts in this budding new field. I won't go through the details. This is just lists of names and years. They went in and they did detailed numerical analyses. The key person who really did the most was David Garfinkel at Oakland University in Michigan. The key person who really formulated the program was Beverly Berger, who became the program director for gravitational physics at NSF and was our program director in the period leading up to our discovery of gravitational waves. So, but what they discovered through numerical simulations is the Russians were right on, except for a few little things they had missed, like spikes, occasional spikes that came at the end of one of these oscillations. And so, I had guessed the Russians were right, but that's because I'm not a very rigorous physicist. I'm happy to accept levels of rigor that are lower than most of my colleagues. So I took pride in having guessed right, but if I'd been wrong, it wouldn't have been any skin off of my back. Anyway, so. But that turns out not to be the whole story. I'm going to tell you the rest of the story of geometrodynamics near singularities by appealing to the movie Interstellar. And in the movie Interstellar, Matthew McConaughey, playing Cooper, goes inside a black hole. This is an embedding diagram for the shape of space around the black hole. I'm not going to go through the details of this for the moment. Through the horizon of the black hole, and and it turns out that below him is this BKL singularity, and he's headed right toward it. And a certain death, to be stretched and squeezed to oblivion. But time is so distorted down in here that everything that falls into the black hole after him comes crashing down toward him in a fraction of a second, as seen by McConaughey. Billions of years in the future, everything that falls into the infinite future comes crashing down basically in a fraction of a second and creates basically a shockwave type singularity falling onto him from behind, and one where there is a stretch in the up-down direction, squeezes in east-west and north-south, but the double time integral of the acceleration of the tidal force is finite. What that means is he gets stretched, but he isn't infinitely stretched by the time the singularity is reached, so he might still be alive. And this is a very surprising behavior. This is what is called in the movie a gentle singularity by Romilly, who's the theoretical physicist, gets killed by Kip. But then there's another singularity. The infalling singularity was discovered by Eric Poisson and Werner Israel in Canada in 1994. And then outflying singularity discovered by Donald Merolf, who's at Santa Barbara, and Amos Ori, who's at the Technion in Israel in 2012, discovered through mathematical analysis. Everything that fell into the black hole in the distant past, a tiny bit of it scatters back up toward Cooper, toward Matthew McConaughey, and scatters back up and arrives in a fraction of a second in the form, again, of a shock wave that has a similar kind of a character. And so Cooper is caught between these two singularities, which mathematically are null singularities for physicists. They're light-like singularities, not space-like singularities. And so those are the singularities that Cooper has to run into, one of them, and conceivably he could survive, and in the movie he does survive. Okay. So we now understand, in fact, that it appears there are 3 different singularities inside a black hole, and interesting dynamics of curved space-time, geometrodynamics in each of them. We aren't 100% sure of the story I have told you because, again, this story is worked out by approximation techniques, and we need some numerical simulations of the interiors of black holes to be sure of this. Okay, so that's the first venue for geometrodynamics that I wanted to talk about. The second venue is imploding waves and what's called critical collapse. This is work that was done beginning with numerical simulations when the simulations were just good enough that you could begin to do interesting calculations. You could do 2 plus 1 dimensional calculations, things where there was at least axial symmetry. So you had time plus 2 non-trivial spatial dimensions in your calculations. And you begin with a wave, and the original work was done by Matthew Choptuik using a scalar wave, which is the standard scalar wave equation with no nonlinearities in it. And the scalar wave is given some sort of arbitrary profile and some amplitude. And what the scalar wave does is it implodes from all directions. I'm just showing it the wave in a horizontal plane, but it's imploding from all directions spherically, in this case spherically, to make the calculation, the numerical calculation simple. And as it gets implodes, it gets stronger and stronger. Any imploding wave will get stronger and stronger as it implodes. And its energy density then rises, and that energy density creates space-time curvature, and the wave then interacts with the curvature. That's the source of the nonlinearity. And something very strange and interesting happened. When the amplitude of the wave, and this doesn't matter what the shape of the wave was at all, but there's always a critical amplitude. When the amplitude was bigger than this critical amplitude, the wave went in, and the energy was so great in a sufficiently small region that it made a black hole. And the mass of the black hole is proportional to the actual amplitude of the wave minus the critical amplitude raised to some power. And from the numerical simulations, the power was 0.374. When the amplitude was less than this critical value, the wave just went in and dispersed, came back out. But it did create some strong space-time curvature, and the radius of curvature, something that to physicists has the same dimensions as a mass because we set Newton's gravitational constant, the speed of light, to unity. Excuse me for the non-physicists. Anyway, this quantity scales with the same power, the difference between the critical amplitude and the actual amplitude of that same power beta. And so here's a critical behavior. There's a critical exponent that governs how strong the space-time curvature is if it's not strong enough to form the black hole at the maximum point, the maximum space-time curvature that you get before the wave disperses, or the mass of the black hole that forms. When the amplitude is precisely equal to the critical amplitude, something really interesting happens. I show it here heuristically. The waves go in, and then space and time, in some sense, sort of boil. You get what is a discretely self-similar behavior you get a structure formed in here that repeats on smaller and smaller scales, going all the way down to the center, where there's actually a naked singularity. And for those, singularity that's not hidden behind a black hole horizon. An infinitesimally small naked singularity, but one that was sufficient to for me to win a bet against Stephen Hawking about whether naked singularities can exist, according to the laws of physics. The waves then come out with shorter and shorter wavelengths in this discretely self-similar form as time passes. And in a finite length of time, you form this naked singularity. Though that was a practice problem, it was not geometrodynamics. And so Andrew Abrahams and Chuck Evans went in, and later Yevgeny Sorkin with higher precision, and did the same thing with gravitational waves. So now you have no matter present at all, nothing except gravitational waves, ripples in the shape of space and time. Imploded these gravitational waves, not spherically now, but actually symmetrically, because you cannot have a spherical configuration of gravitational waves. And lo and behold, the same behavior. You form a black hole if the amplitude is bigger than some critical amplitude, the same within the numerical accuracy, the same critical exponent. If the amplitude is less than the critical amplitude, the wave disperses, and the maximum curvature that's achieved behaves in the same way. And moderately strong evidence for this boiling that I talked about at the critical value. And so these kinds of behaviors are similar to what occurs in a phase transition in condensed matter physics. You have critical behavior and scaling, and that's what occurs in phase transition. This is basically a phase transition in the structure of warped space-time without any matter being present. And so this is the second really interesting thing we learned about geometrodynamics. The first one, the first example that I gave you, we learned that you can have chaotic behavior governed by chaotic mathematical maps in geometrodynamics. Here we learned you can have critical behavior like in condensed matter physics. Numerical studies of this are still in their infancy, and I think there's a great richness in this area to be uncovered. Now let me turn to the most interesting, I think, of my examples, which is geometrodynamics in colliding black holes. This is a diagram that was drawn by an artist that, based on a sketch of mine when we were originally proposing to build LIGO. And we said that one of the most interesting sources of gravitational waves will be two black holes that orbit around each other. And so this is a depiction of the curvature of space or warping of space around two black holes as seen from a higher dimension. The two black holes go around each other, collide and merge, produce gravitational waves that go traveling out into the universe. And we estimated that the strength of those waves, the strongest waves that you would see, would be about 10 to the minus 21 in dimensionless amplitude. I don't want to go into the details of this. Those estimates were made around 1978. And the first thing that we saw with LIGO in 2015 was waves from a colliding black hole with amplitude precisely 10 to the minus 21. So our guess in 1978 was a lucky guess, but we knew that was the right ballpark. When I say our, this was at a conference of all the people who were working in the field at that time, theorists and experimenters, where we spent a week basically brainstorming about sources of gravitational waves. This is a very interesting source of gravitational waves because we now know, we knew this roughly already way back in, to order of magnitude, way back in 1978. But we now know from numerical relativity, the actual number, that the total power output in gravitational waves from such a collision is 50 times higher than the luminosity of all the stars in the universe put together. And if these are small black holes, the collision lasts for a very short time. The power is 50 universe luminosities. It lasts for a very short time, so the total energy that comes out, the time integral of the power, is about roughly 5% of the mass of the black holes. If the black holes are really heavy, like the ones in the centers of giant elliptical galaxies, then the collision will last for many hours. And its power output is 50 universal luminosities, and the total energy is, again, about 5% or so of the energy that comes of the mass of the black holes. And so this is quite interesting from that point of view. And there's no electromagnetic waves emitted whatsoever. The electromagnetic astronomers have not seen any electromagnetic waves from the colliding black holes that LIGO has detected. Though it's possible that if you have a disk of hot matter, an accretion disk around the binary, that when the binary merges, it will disturb the accretion disk enough that you might get some electromagnetic emission, but that's not been seen. That's a hope for the future. The details of the collision, which are the geometrodynamics that I want to focus on, are encoded in the gravitational waves shapes, their waveforms. And so this is why I'm really interested in this, is to understand geometrodynamics through black hole collisions. So we were only able to understand those details theoretically by numerical relativity simulations. And so I'm going to show you now a simulation done by the SXS collaboration, which is Cornell, CalTech, CETA in Canada, Cal State Fullerton, Oberlin, Washington State University. It's a collaboration of numerical relativity experts led by Saul Tucholsky. And this is their simulation of GW 150914, the first black hole collision that was seen by LIGO. And I'm going to show you then a depiction of the space-time geometry or metric in the orbital plane of the two black holes as they go around each other and collide. So this is what we learned from the numerical relativity. And so this is what it looks like if you're looking in from a higher dimension. Each black hole has a shape of space that looks like a funnel. You've seen black holes depicted in terms of funnels. That's what a black hole would look like if you lived in a higher dimension, looked in on our universe. And we're looking in on just the orbital plane. The color coding is the slowing of time, and the arrows are the dragging of space into motion. More precisely, the shape of space describes the shape of the surface describes the two-dimensional metric of the orbital plane. The color coding describes the so-called lapse function, and the arrows the so-called shift function, which are pieces of the space-time geometry. There's a slight cheat here, and that is that although you can always take a two-dimensional surface that's warped and embedded in a flat higher dimensional space locally, you can't do it globally. You go around the black hole and it doesn't match up smoothly. And so there's been a cheat done to deal with that, and the cheat is described right there, and I can discuss it with experts afterwards if you wish, but it's just in all due honesty. So I want you to watch what happens. This is Geometrodynamics in the flesh, in the movie. It's the movie version. This is what we saw, what produced the waves that we saw, the first waves. Now, it's gone into slow motion. The shape of space is creating something that's rather like the splash in a giant ocean wave in a storm at sea. The color coding, red, time is slowing very slowly in the red region. It oscillates, and waves go propagating out, gravitational waves propagating out into the universe. So that is a depiction based on a numerical simulation of geometrodynamics. And it was very exciting to see. And it was wonderful to have this simulation and go look at the gravitational waves that were seen, the wave shapes, and then go back and be able to say, this is what those wave shapes are telling us. The problem, however, is that there's too little of the space-time geometry depicted in this way. You're only getting 2 dimensions out of 3 spatial dimensions, and you're missing, as a result, a number of very interesting things. And so, in order to really understand what's going on, together with a set of CalTech graduate students and postdocs, and former graduate students and postdocs, who are spread around the world, CalTech and Cornell and South Africa at the time of we published this. We devised a way to visualize something called the Riemann curvature tensor of general relativity. And so let me explain what this is. So I'm going to explain by analogy with electromagnetic theory. So if I begin, it turns out that the electric field and the magnetic, and I'm going to get technical now here for a few minutes. The electric field and the magnetic field do not exist independently of the observer. You have to choose a reference frame before you ever know what the electric field and the magnetic field are. In other words, you have to decide what set of slices through space-time you're going to regard as simultaneous. You're going to have to pick a space-like surface in space-time, time going up and space going horizontally. Once you have done that, then the electric field lives in this surface, your surface of constant time, and the magnetic field lives in this surface. And the electromagnetic field tensor, second-rank symmetric tensor, splits up into the vector electric field and the vector magnetic field, which we visualize using field lines, such as the magnetic field lines around the surface of the Earth. So this is by way of background for the physicists and other physical scientists. In general relativity, the local space-time curvature is described in terms of the Riemann curvature tensor, which is the same thing as something called the Weil curvature tensor in vacuum when there's no matter present. And I have no matter present in this discussion. And that, when you pick a reference frame or choose a three-dimensional surface in space-time, splits up into two parts, which are symmetric trace-free tensors, or think of them as symmetric matrices. And one of them describes tidal forces or tidal accelerations. And so this second-rank symmetric tensor or matrix, if you multiply a separation vector between 2 points in space-time, in space, this separation vector C, into that tensor or matrix, throw on a minus sign, that tells you the relative acceleration of freely falling particles at these 2 points. So this tidal field describes then the stretching and squeezing, the stretching between my wife's head and her feet, the squeezing from the sides. The other piece of this space-time curvature is we call a frame drag field. It describes differential frame dragging. So if I put a gyroscope at this point in space, another gyroscope at that point in space, this gyroscope will precess around and around, just behaving inertially relative to that gyroscope. Because of dragging of space into motion or dragging of inertial frames. And the angular velocity of precession is obtained by multiplying the separation vector into this frame dragging field, second-rank symmetric field. So I've given these details for physicists so they have some sense that what's going on here is similar to electromagnetism, and there's some deep underlying mathematics. Okay, now let me describe what goes on physically near a black hole. If I put my wife above the black hole with her feet pointing down, she gets, if this black hole is spinning rapidly, she doesn't get stretched like you might have thought. She gets squeezed from head to foot rather strongly. But if she's above the equator, she's stretched. Why? That's not the story you usually get, but it's because the black hole is spinning, and that turns out to switch things around. So she's stretched squeezed from head to foot at the North Pole, stretched at the equator. And the magnitude of this, the relative acceleration between her head and feet divided by her height, is what we call the tendicity, and it is the normal component of this tidal field. And it is that tendicity then that produces the stretching and squeezing. And so we think of the black hole as having a squeezing tendex. Tendex comes from the Latin word tendere, to stretch. But this is a squeezing tendex at the North Pole, a squeezing tendex at the South Pole, and a stretching tendex in the equator, in the equatorial regions. And outside the black hole, there are tendex lines, which are integral curves of the eigenvectors of this tidal field. And the tendicity is an eigenvalue, again, mathematics for the physicists. The key thing is that there are lines analogous to magnetic field lines or electric field lines. And my wife, gets stretched along the red lines and squeezed along the blue lines. And you see a pattern of red and blue lines that she gets stretched and squeezed along. And there are lines that have particularly strong stretching and squeezing, and we call those tendexes or tendices. It's a collection of tendex lines with large tendicity. And so sticking out of this black hole, there actually is a fan-shaped tendex that stretches my wife. And then there is a poloidal thing, sort of like the magnetic field lines of the Earth, that is a squeezing index that goes from the north polar region to the south polar region. And these things just stick out of the black hole. We never knew about them before until we did the simulations and then went in and looked at mathematics. But we were motivated by the simulations to understand the mathematics. But there's more to this. If my wife hangs above the northern regions of the black hole and puts a gyroscope at her head and a gyroscope at her feet, her head sees her feet gyroscope precessing around and around in a counterclockwise direction. And her feet sees her head gyroscope going around in a counterclockwise direction. This is like taking a wet towel and you squeeze water out of the wet towel and you think about it. If your right hand sees your left hand going counterclockwise, then your left hand will see your right hand going counterclockwise. So there's a helicity, we use the word helicity, to the twisting. So there's a twisting then of space in that sense in the North Pole, governed by this horizon vorticity that is a piece of this frame drag field. And at the South Pole of the black hole, there is a clockwise twisting of space. And so we have a counterclockwise vortex of twisting space at the North Pole, a clockwise vortex at the South Pole. And sticking out of the black hole, it turns out, there are vortex lines, rather like the vortex lines that you deal with in fluid mechanics. Counterclockwise vortex lines sticking out of the North Pole, clockwise vortex lines sticking out of the South Pole. And my wife, gets twisted by those vortex lines. Those vortex lines are mathematically the integral curves of an eigenvector of the frame drag field. Again, just for the physicists, so an engineer, so they have some sense of the mathematics that underlies this. This is mathematics that was never really worked out or thought about until we saw these phenomena in our simulations. And so for a rapidly spinning black hole, then, the vortex lines that twist my wife in a clockwise way come out of the south polar regions, go around the black hole and back into the south polar regions. The ones that twist her clockwise come out of the north polar regions, go around the black hole, and go back into the north polar regions. Physical phenomena made from warped space-time that are attached to the black hole that we didn't know about until the simulations. We refer to a counterclockwise vortex as a set of vortex lines with very strong twisting, and clockwise vortex. So there's a counterclockwise vortex sticks out of the North Pole, clockwise vortex out of the South Pole. Those are the only pieces of this story that I'm going to really focus on, really going to need, is these counterclockwise vortex at the North Pole, clockwise vortex at the South Pole. But all the rest of this is there as well. Okay. So now let's look at a head-on collision between two black holes with a blue vortex sticking up here, a red vortex sticking up there, and they come crashing together, and when they come crashing together, they form a black hole horizon, a merged black hole horizon. This is the horizon, the point of no return, the surface of the black hole. And we now have a black hole horizon that has 4 vortices sticking out of it. One clockwise twisting vortex, 2 clockwise twisting vortices, and 2 counterclockwise twisting vortices. Now it turns out black holes don't want to have 4 vortices. At maximum, they only are allowed to have 2 vortices. And so these vortices fight with each other to see who wins and wind up with just 2 of them. And so now I'm going to show you, without showing the vortex lines sticking out, what happens. So just remember, you've got a blue vortex of twisting place up here on the right. Now it's red. Now it's blue. Now it's red, and so forth. So what's going on? Whenever it goes green, the vortex lines have popped off of the black hole. And if my wife is there, she's not going to feel any twisting when it goes green. And so here it is, I'm repeating the movie there, and I'm showing you a still here at a moment when you have the blue vortex up there and the red there. The vortex lines have reattached. The vortex lines, clockwise vortex comes out of that blue vortex on the black hole, goes around, goes back into the blue vortex on the backside. The red vortex lines go around back into the red vortex on the backside. So you have these vortices sticking out of the black hole. But every time it goes green, they pop off, they embrace each other, and they form a smoke ring of twisting space that travels out at the speed of light, of embraced vortex lines. And as it travels outward through an analog of the Maxwell equations, these vortex lines generate Tendex lines of stretching and squeezing space. And so you have this ring, or like a smoke ring, that has entwined vortex lines of both helicities and Tendex lines stretching along this direction and along that direction. And that is a gravitational wave. Sorry. And so this is one method of creating gravitational waves. And it's created by these vortex lines, that were attached to the black holes. The black holes collided, the vortex lines popped off, embraced each other, traveled outward, and induced Tendex lines to join on. This is geometrodynamics of the most interesting sort that we have run into. And we had no idea this was going on until we did the simulations. If you have an orbiting collision, it's rather different. The vortex lines stick out of the black hole and stream along behind the black hole as the black hole spins, rather like water from a whirling sprinkler. And as they travel out, they induce Tendex lines around themselves, as in the previous case. And so I'm going to skip over this, and I want to get on to gravitational wave observations. But what I've done is given you some sense that there's a real richness to geometrodynamics that we didn't know about. There are these vortex lines, these vortices and these tendencies that stick out of black holes as physical structures, as real as the Earth's magnetic field, that are responsible for generating gravitational waves when black holes collide. Observations. This is one of the two LIGO gravitational wave detectors in Hanford, Washington. And the challenge now is from observed binary black hole gravitational waveforms. How can we read off the geometrodynamics that produced them? That is, the dynamics of the vortices and tendencies near the black hole that generated the gravitational waves. And the answer is simple. You simply identify the binary black hole parameters, their masses and spins of the black holes, by comparing the observed waveforms or wave shapes with the waveforms from simulations. And then you just go back to the simulations and see what was the dynamics of space-time, the geometrodynamics that produced those waves. So here are gravitational waveforms. Every source of gravitational waves has two waveforms, just like there are two polarizations of electromagnetic waves. This is for a small black hole merging with a large black hole with spins in some random orientation, a random direction toward Earth. And the waveforms can be rather interesting, though the ones that we have seen thus far are much simpler than these. And so you do a simulation, you generate waveforms, you go in, you compare the observed waveforms with the results of simulations, go back and infer the masses and spins of the black holes. So we have seen 6 binary black holes so far. There are only 5 of them shown here. By the time the 6th one came along, this was getting to be sufficiently routine that there was no press conference, as I recall. It was just put on the archive. The paper was put on the archive for physicists to read. And it was not even brought into this. And so these are the actual waveforms that were observed from these 5 of the 6, not the last one that was found. The first one was 2 black holes, one 36 times as heavy as the Sun, the other 29 times as heavy as the Sun, 1.3 billion light years from Earth. Then you can go on down. Here's a waveform that lasted for a very long time, and the reason is because the masses were much smaller, 14 solar masses and 7.5 solar masses. And so there was much more of the waveform, it turned out, in the LIGO frequency band to observe. And so we saw about 1.5 seconds of waves here, whereas we only saw about a few hundredths of a second of waves in the first one. And so we are beginning to have a rich set of observational data. The LIGO detectors are shut down and are being improved, cleaned up. They're not at their design sensitivity. They're being cleaned up and brought toward their design sensitivity. Once they're at the design sensitivity, we will be seeing somewhere between 10 and 30 times as many as faster rate or larger. Well, let me start over again. Let me say it this way: that when LIGO was up and both detectors were running during our observations thus far, we were seeing roughly 1 black hole merger per month. When we can see 3 times farther at design sensitivity, 2 or 3 times farther, we will see a volume of the universe that is 2 cubed, which is about 10, or 3 cubed, which is about 30 times bigger than we were seeing. And so instead of 1 a month, we'll be seeing a few a week or 1 a day. That's about 2020. And there are plans to upgrade the LIGO detectors, tentative plans, that will lead us to see 10 times farther than that, 30 times farther than we now see into the universe by the mid-2030s. That means event rates 1,000 times bigger than in 2020. That means actually seeing every black hole merger in the universe with masses below about 1,000 solar masses. And it's really exploring not only geometrodynamics, but the processes that form black holes through population statistics and so forth. And for all of these, there was excellent agreement between the observed and simulated waveforms. And so you could go in, and with each of these, you could see what was the geometrodynamics that produced the gravitational waves that were observed. So I'm getting near the end of this. I want to address the following issue, that in 1984, I speculated that the shapes of the gravitational waves we would see would be interesting like that. And I wrote that down, and that was sort of shown in all the talks that I gave and other people gave from then until we saw the waves. The waves are not really all that interesting. The shapes we've seen thus far were much simpler. And this was a big disappointment to me. I mean, you can't have everything. Nature was awfully kind and gave us gravitational waves, but geometrodynamics in terms of the shapes of the waves was much less interesting than it could have been. Why? Because the disturbances, when you form a when the black holes merge, the disturbances, the geometrodynamical disturbances, they are radiated away. They just fly away very rapidly. They depart. Some of the disturbances go down the merged black hole. Some of the disturbances go off far away. The disturbances being these vortices and tendencies and the manners in which they're excited. The excitations disappear awfully darn fast. However, Juan Yang and Aaron Zimmerman, who were 2 graduate students of Yanbei Chen, who's my successor at CalTech, together with Louis Lehner, who is a masterful numerical relativist, and they are masters of the analytic side of things. In 2015, at about the same time as we discovered the gravitational waves, they made a discovery theoretically of the following sort. We already knew that if you have a slowly spinning black hole, the shape of space around it looks like this. It's sort of a trumpet horn. This goes out and flattens out when you get far away. This is as seen from a higher dimension. The faster the black hole spins, the longer the throat. In black holes up to spins of 0.998 are what we expect. It might go a little higher, but not a lot higher than that. So with this long throat, it's possible for waves to be trapped in here for quite a while. And what Juan Yang and Aaron Zimmerman did was prove that that was the case analytically. And if they're trapped in here for quite a while, then they have the possibility to interact in a nonlinear manner. Wave-wave coupling, nonlinear wave-wave coupling, which is something that plays a big role in modern optical technology. Nonlinear wave-wave coupling plays a big role in plasma physics, plays a big role in fluid mechanics and turbulence. The analysis they did analytically, together with numerical work from Louis Lehner, showed that what you will get is an analog of 2-dimensional turbulence. You begin with 2 waves, and they interact, and in a 3-dimensional turbulence, which is what's familiar that you normally see, they interact and they produce, and their energy cascades to a smaller length scale. But in 2-dimensional turbulence, which occurs in here, the energy cascades to a larger length scale. So you have two waves that have very short wavelengths in here that have been created as part of the Geometrodynamics. They interact, they produce a wave of longer wavelength. Several of those interact, produce waves of longer wavelength. And there's a cascading of energy. It's an analog, as I say, of turbulence. And this is really exciting to me, the possibility that you have the analog of turbulence, albeit perhaps less interesting turbulence because it's cascading in the inverse direction. But still, this is something that we have a real shot at seeing ultimately when we have someday see a sufficiently rapidly rotating black hole and have good enough signal-to-noise ratio. I think we're likely to see gravitational waves produced by two-dimensional turbulence around the merged black holes. So just to summarize then, I've described four current arenas for geometrodynamics: singularities, imploding waves, colliding black holes, and gravitational wave observations. This is really a very young topic, even though it was originally proposed by John Wheeler 60 years ago. I suspect we've barely scratched the surface, but we are beginning to learn about what nonlinearities do to warp space-time in the absence of matter. Thank you.
Well, thank you for that very beautiful talk. We have time for a few questions. B.
Michael, what physically are you measuring? What physically are you measuring? I thought it was a motion of one point relative to another point.
You're measuring the tidal force, the stretching and squeezing tidal force of the gravitational wave. So the gravitational wave comes along and it stretches and squeezes space between the two ends of the detector. It's the same thing as the stretch and squeeze of my wife as she's near a black hole, or of the Earth's oceans by the moon and the sun. And the mirrors, this is a high frequency motion, frequencies high compared to the 1 hertz swinging frequency of a suspended mirror. And so the gravitational, and so what happens when is that the mirrors ride on the stretching and squeezing space, they're pushed back and forth. Another way to say it is when I talk about space stretching, what I mean is that inertial reference frame there, inertial reference frame here, move apart and move together. Inertial reference frames are markers for the space. You put the inertial reference frames at rest with respect to each other and they become markers for the stretching and squeezing of space. Space stretches, these mirrors move back and forth because they're behaving inertially at frequencies above 1 hertz swinging frequency. And so you're seeing, another way to say it is you're seeing the tendencies of stretching space and squeezing space associated with the gravitational wave.
Next question.
Taking this back a little bit toward the Big Bang, now that we have a slightly better understanding, would any of this, if there are, for example, primordial black holes, say as dark matter candidates, might any of this give us an idea of something we might potentially see in the cosmic microwave background?
So the cosmic microwave background is capable of showing us only gravitational waves that have wavelengths that are pretty big on the sky, which means wavelengths that are, say, 100 million light years or longer. It means they oscillate with periods of 100 million years, which is a little longer than a graduate student lifetime, so you don't want to sit there and try to measure the oscillation. So you see the pattern in the polarization on the sky. At those kinds of wavelengths, we do not expect there are any black holes that produce things with such long wavelengths. Those are the wavelengths that are expected to be produced in the birth of the universe. So by looking at the cosmic microwave background, we are trying to see indirectly primordial gravitational waves that came off of the Big Bang that were then amplified by the phenomenon of inflation in the very early universe. And so I've talked today primarily about LIGO, which looks for gravitational waves with periods of oscillation of about 100th of a second. This cosmic microwave background polarization looks for gravitational waves with periods of millions of years, hundreds of millions of years. A space-based analog of LIGO called LISA, spacecraft that track each other with laser beams, will look for gravitational waves with periods of minutes to hours. And yet another technique involving the timing of pulsars. So signals from pulsars, very regular space pulses coming to Earth from different directions on the sky. If the Earth's gravitational wave sweeps across the Earth, it speeds up and slows down clocks on the Earth, making it look like all these pulsars are slowing down and speeding up. It's a slightly heuristic description, but that phenomenon, by that we will see gravitational waves with periods of a few years. And all of these different types of gravity wave observations will be in process. We'll be collecting data within the next 20 years. So we will have 4 different frequency bands. It's analogous to turning on radio astronomy, X-ray astronomy, gamma ray astronomy, and optical astronomy all within 20 years.
That's great. Another question?
Okay, I have a couple of short questions. First one that's more important. When you say that rapidly spinning black holes will have the squeezing 10x forces above their poles, how rapidly spinning are you talking about? What kind of spin parameter? Like, I'm curious, like, how relevant this is in an astrophysics context. Like,
I forget the precise number, but so if you're an astrophysicist, you're accustomed to some dimensionless parameter A, which appears in the Kerr metric. So I'll answer it by connecting to something else you might know about. In regions where the shape of the horizon is that concave? Concave, I guess.
convex, I think.
Whatever that is.
Pretty sure
like
that's
that.
convex.
Then you get stretching at the horizon. If it spins fast enough, it bends in the other direction at the poles, and you get squeezing. And so it's the transition is where there's a transition from being concave to convex at the poles, and that's a spin of something like 0.87. I forget, 0.83. It's 0.8 something. So it's very relevant astrophysically. There's speculation that most black holes in the universe spin faster than that, and so most likely have the squeezing tendencies sticking out of the poles instead of stretching tendencies.
The other question I have is, you state that with the BKL singularity, like, your neighbors would not be able to communicate, you wouldn't be able to communicate with your neighbors. Is that true of the other 2 singularities that you mentioned as well?
Yes. No, let me back up. I'm not saying it quite right. No, I don't know. I don't know. It was key to being able to do this approximation technique in order to do the mathematics for the Russians, and it underlies it. The analysis that was done for the other 2 types of singularities is a very different kind of analysis, and I don't know. I think so, but I'm not sure. Yeah.
Was there any significance in the LIGO announcement on February 11th? Like, what was the reason why it was held on that day?
Because we were ready. The date was negotiated between the LIGO team, Physical Review Letters, which was publishing the paper on the day of the announcement, the National Science Foundation, leadership of the National Science Foundation. It had to be late enough that the paper had been refereed and accepted for publication, ready to go out online at the journal, and had to be a time that worked for our friends in Washington. So that was about 4 months after the discovery. The discovery was in September, October, November, December, January. It's about 4.5 months after the discovery. Why so long? Because it was such a momentous discovery, we had to be absolutely right and sure there was nothing going wrong with the detectors. Just to give you some sense of what that meant, these gravity wave detectors are so complex that coming out of them, there are 100,000 data channels, each of them carrying information about either what's going on in the environment or inside the detector. And we had the team, when I say we, I mean a handful of key experts among the younger generation. I'm the old geezers. So among the younger generation, had to go in and look very carefully at data channels that carried crucial information to be absolutely sure the detector was working properly and that nothing was wrong anywhere in the detector. That took quite a while to do. And then it also took quite a while for the team of 1,000 people to agree on the wording of the paper.
Okay, well, let's thank Kip again.